SQL Server and Azure SQL. SQL Server and Azure SQL Performance Playbook Audio Learning Guide. Welcome to this long-form walkthrough dedicated to SQL Server and Azure SQL Performance. Think of it as an audiobook script you can read now and listen to later. I'm assuming you're a .NET developer who's comfortable wiring up EF core, writing stored procedures when you must, and debugging the occasional query. But you haven't spent years on the DBA side of the fence. The goal here is to give you the confidence to survive interview conversations about query tuning, indexing, and Azure database options, even if you haven't lived and breathed them in production. By the end, you should have a vocabulary for describing your approach, practical examples you can reference, and mental models you can apply immediately. Before we dig into the tactics, remember that SQL performance is about cost, not ego. A slow query wastes CPU, I/O, and memory. A missized Azure tier wastes money. A missing index becomes a reliability incident when traffic spikes. Interviewers want to know that you can connect those dots, read a plan, reason about data shapes, and pick the right cloud knob to turn. We'll walk from core SQL Server mechanics to cloud-native enhancements so you can articulate both worlds. Why performance conversations matter. Performance troubleshooting can feel mysterious because databases are opaque boxes. You send an ORM query and hope the engine figures it out. Under the hood, though, SQL Server is a cost-based optimizer that builds execution plans using statistics about your data. When interviewers ask you about performance techniques, they want to check whether you understand how to give the optimizer what it needs and how to measure the results. Imagine joining a 10 million row orders table to a 1,000 row customers table. If your predicate filters orders down to 100 rows, the optimizer may choose a nested loop join. If your predicate is non-sargable, maybe you're wrapping the order date column in a function, it may think it needs to scan the whole orders table. The difference is seconds versus minutes, and potentially the difference between fitting inside a business-critical Azure tier or burning money on hyperscale just to compensate. Performance conversations matter because they influence architecture choices, cloud bills, and user experience simultaneously. Another reason to learn this material is that modern teams expect engineers to be full stack beyond just the UI. You might not manage backups, but you should know when to suggest a covering index, when to enable query store, or when to turn on automatic tuning. When you describe these techniques clearly, you signal that you can handle production traffic without babysitting. Indexing strategy fundamentals. Indexing is the foundation of query performance. The most common interview question is, how would you choose an index for a slow query? Start by distinguishing clustered and non-clustered indexes. The clustered index defines the physical order of the table and is effectively the table itself. By default, SQL Server uses the primary key. Interviews love when you mention that a clustered index should be narrow, ever-increasing, and unique to avoid page splits. Identity columns or guides generated with new sequentialid are classic choices. Non-clustered indexes sit beside the table and contain copies of the indexed columns plus a pointer, the clustering key, back to the base rows. When you run a query that only needs the indexed columns, SQL Server can satisfy it entirely from the index without touching the table. That's called a covering index. Explain that when you're tuning a report query that filters by customer ID and order date and returns order total and currency, you'd consider an index on customer ID, order date, with include order total currency, so the query becomes a single index seek. Avoid over-indexing. Every index increases write cost because inserts and updates must maintain each structure. Interviews appreciate hearing that you weigh read benefits against write overhead. Mention maintenance too. Indexes fragment. And in Azure SQL, you typically schedule maintenance or let automatic tuning handle it. If you can cite a real experience, maybe you added a filtered index on status equals pending to accelerate a queue dashboard, do it. Filtered indexes are a quick win because they let you avoid scanning inactive data. Finally, call out column store indexes. For analytics or reporting workloads, column store compresses data and stores it by column rather than row, enabling massive scans with vectorized execution. Azure SQL tiers from general purpose upward can use clustered column store indexes, and they're incredible when you're aggregating billions of rows. They do make writes slower, so they're best for append-heavy or batch-loaded tables. Query shape and plan analysis. Once indexing basics are on the table, talk about how you inspect execution plans. SQL Server Management Studio, Azure Data Studio, and even Set Statistics XML. On give you the plan. Interviewers want to hear that you don't guess, you measure. Describe how you look for red flags, table scans on big tables, key lookups that happen thousands of times, or huge estimated row counts that don't match actual row counts. A key concept is query parameterization. When a plan is compiled, SQL Server uses parameter sniffing to guess row counts based on the first parameter values it sees. In OLTP workloads, this is usually good, but sometimes one fat parameter, say a customer with millions of orders, produces a plan that performs terribly for everyone else. Explain that you can fix that with option recompile for truly dynamic queries, or by using optimize for hints, or by rewriting the query to use local variables so each execution compiles its own plan. Azure SQL's automatic plan correction can also detect regressions and force a previous good plan. This is also the place to mention Query Store. It's basically a flight recorder for plans and runtime stats. When a deployment introduces a regression, Query Store lets you compare plans side by side, see which plan I'd performed better, and force the better one. In an interview, you can describe enabling Query Store in read-write mode, capturing information over a week, and using it to justify adding an index or rewriting a query. When you're prepping for questions, memorize the steps, capture plan, analyze high-cost operators, validate with actual runtimes. Sargability and predicate craftsmanship. Sargable stands for Search Argument Able. Predicate sargability is the difference between an index seek and an index scan. Use verbs like avoid wrapping columns in functions, and you'll sound like you've lived it. Practical example, you have a where year order date equals 2023. Because you applied year to the column, SQL Server can't use an index on order date. Rewriting it as where. Order date greater than or equal to 2023-01-01 and order date less than 2024-01-01 restores the index seek. This also applies to implicit conversions. If customer id is an INT, but you compare it to an nvarchar parameter, SQL Server must convert every value in the column, again forcing a scan. The fix is to pass correctly typed parameters or convert the literal, not the column. In interviews, mention that you've seen CPU spike because an ORM built where customer id equals at P0 with at P0 typed as NVARCHAR. Even though the text looked identical, the implicit conversion sabotaged performance. In general, keep predicates simple, where last name like Macasent is sargable, where left, last name 3 equals Mac is not. Avoid wildcards at the beginning of strings, %foo because indexes can't help. They'd require scanning the entire column. For geospatial or range queries, consider computed columns. You can pre-compute something like order year int generated always as year order date and index it while keeping the original column intact. That lets you use friendly query syntax while still getting an index seek. Data types, implicit conversions, and parameter sniffing. Data types feel boring until they bite you. Choosing the right type affects storage, memory grants, and even network throughput when data travels between application and database. Interviews appreciate when you mention use the smallest type that fits and avoid mixing data types in joins. Example, storing a phone number as NVARCHAR 4000 waste memory and prevents index compression compared to CHAR10 or VARCHAR 15 with a check constraint. Implicit conversions, as mentioned earlier, show up in execution plans as warnings. They can force index scans or sort operations because the engine must convert values row by row. When you describe troubleshooting, say that you look at the plan's warning icons, hover to see the Convert Implicit message, and then align your parameter types. Parameter sniffing is another subtlety. Suppose you have a stored procedure, USP get orders, at customer ARD ENT. The first time it's executed, the optimizer sniffs the parameter value, say 1, and builds a plan optimized for small row counts. If customer 1 only has 10 orders, the plan might choose a nested loop join. Later, customer 42 with 1 million orders runs the same procedure and reuses the cached plan, now executing slowly. Solutions include creating separate procedures for big and small customers, using option recompile for the statement that varies wildly, or using optimize for unknown. Interviewers want to hear that you understand the trade-offs. Recompilation costs CPU, but that's sometimes cheaper than running the wrong plan for 1 million rows. Stats maintenance and cardinality confidence. Statistics tell the optimizer how data is distributed. They're histograms on columns or column prefixes. Without fresh stats, the optimizer guesses wrong, leading to memory grants that are too high, causing spills, or too low, causing row-by-row execution. Mention that SQL Server auto-updates stats when about 20% of a table changes, but on big tables that threshold is huge. For a 100 million row table, you'd need 20 million changes before auto-update kicks in, so you schedule manual updates or use AUTO _UPDATE _STATISTICS _ASYNC in Azure SQL to keep up. Explain how you use update statistics with full scan for skewed data or after large ETL loads. In Azure SQL, you can let automatic tuning manage stats, but it's still helpful to know the manual approach for on-prem or when you're debugging. Interviewers may ask how you'd detect stale stats. Answer that you'd compare estimated versus actual row counts in the plan, or query sys.dm_db_stats _properties for last updated timestamps. Also mention cardinality estimation models. SQL Server 2014 introduced a new estimator that handles correlations better, but some legacy databases still use the older model for compatibility. If you ever see a plan misestimate join cardinality dramatically, consider testing the other estimator with Alta Database, Scoped Configuration, Set Legacy Cardinality. Estimation equals on/off. That shows you're comfortable with advanced topics without going too deep. Beating R-bar, set-based thinking. R-bar stands for row by agonizing row, a phrase you'll often see in SQL discussions. The idea is that SQL Server is optimized for set-based operations, not procedural loops. Whenever you run a cursor that updates rows one at a time, you're forcing the engine to re-execute operator pipelines per row. Instead, you can typically rewrite the logic as a single update from or merge statement. For example, suppose you need to apply loyalty points to thousands of users based on their purchase totals. A naive approach is to select users into a cursor, compute the bonus in .NET, and update each row. A set-based approach would be the optimizer turns that into scans, aggregates, and a single update. Besides speed, set-based code benefits from snapshot-based logging and can leverage indexes. When interviewers ask how you'd improve a cursor-heavy stored procedure, say you'd profile it with set statistics, I/O, time on, identify the hot statements, and refactor loops into set operations whenever possible. Concurrency, isolation, and workload patterns. Performance isn't just about single query speed, it's also about how queries behave under concurrency. SQL Server uses locks and latches to protect data. Default isolation is read committed, meaning readers block writers and vice versa. For reporting against transactional tables, that can cause blocking chains. Explain that you can switch databases to read committed snapshot isolation, RCSI, which uses row versioning so readers get a consistent snapshot without blocking writers. Azure SQL enables RCSI by default for many workloads, but you should still mention it. Deadlocks are another interview favorite. Describe the pattern. 2 sessions acquire locks in different orders and wait on each other until SQL Server kills one. You resolve them by keeping transactions short, touching tables in a consistent order, and using appropriate indexes so updates find rows quickly. Mention the deadlock graph, available via extended events or query store, as a debugging tool. Finally, bring up workload patterns. OLTP systems favor many small transactions, while OLAP/reporting systems favor large scans. That's why you'd choose row store indexes and high write throughput for OLTP versus column store indexes and read scaleouts for analytics. Azure SQL lets you deploy read replicas to offload reporting queries, keeping the primary responsive. Azure SQL-specific levers. Cloud interviews almost always jump to Azure service tiers. Azure SQL offers general-purpose, business-critical, and hyperscale service tiers, each with vCore counts, memory, and storage throughput levels. Emphasize that you size the tier based on workload characteristics. General purpose for most web apps, business critical when you need low latency storage and readable secondaries. Hyperscale for multi-terabyte databases that need elastic storage. If you're on the DTU-based model, translate it by saying you look at CPU/IO proportions and use the calculator to pick a tier. Service tier selection ties directly to scaling. Azure SQL lets you scale up or down in minutes. For predictable peaks, say monthly billing, you can scale to more vCores for the event and scale back afterward. Hyperscale even supports named replicas you can route read traffic to. Interviews love when you mention automation, using Azure Automation Runbooks or Elastic Jobs to scale on schedules or metrics. Automatic tuning is another signature feature. When enabled, Azure SQL can automatically create and drop indexes and force last known good plans. You still review the recommendations, but it's a safety net. Mention that automatic tuning should be in automatic mode for dev test to build trust before turning it on for production. If you're worried about regressions, Azure stores verification results so you can see whether a forced plan improved performance. Serverless compute is perfect for unpredictable usage. It auto-pauses after inactivity and resumes when queries arrive. You pay for the storage plus seconds of compute, making it ideal for dev databases or low-volume apps. The key interview point is that serverless still needs proper indexing. Pausing doesn't fix bad queries. You also mention the min-max vCore settings and how you configure auto-pause delays to balance cost and resume latency. Finally, highlight Azure SQL Insights or Azure Monitor integration. Azure SQL Insights provides centralized metrics like DTU or vCore utilization, waits, I/O, and query duration. Pair that with Query Store to identify the statements responsible. Azure Monitor alerts can watch for high CPU, long-running queries, or storage saturation so you can scale or tune proactively. Observability and the Query Store story. We touched on Query Store earlier, but let's dig deeper because it's the anchor for many Azure SQL features. Query Store captures runtime stats, duration, CPU, reads, writes, per query hash, and associates them with plan IDs. When you open the top resource consuming queries dashboard, you can see which statements burn the most CPU or I/O. Interviewers expect you to say you'd identify the top offender, inspect its plan, and optimize accordingly. Beyond Query Store, Extended Events lets you capture deadlocks, wait stats, or parameter sniffing issues. In Azure SQL, the sys.dm_db_wait_stats, DMV reveals where time is spent, memory, I/O, locks. Mention common weights like Pagialatch, slow storage, SOS scheduler, yield, CPU pressure, or LCKMX, blocking. By tying wait stats to actions, adding indexes, scaling tiers, rewriting queries, you show that you can diagnose problems systematically. Azure SQL Insights builds on Azure Monitor to collect metrics across databases. It visualizes CPU, I/O, connection counts, and more. For example, if you see CPU pegged at 90% while I/O sits at 20%, you're likely CPU bound and should tune queries or scale vcores. If I/O is saturated, consider moving to business critical for faster storage or adding indexes to reduce reads. Observability answers the question of whether it's the database or the app quickly, bringing it all together for interviews. Now, let's convert these concepts into talking points you can use in interviews. Start by telling a story. On my last project, we noticed reports timing out. I pulled the execution plan from Query Store, saw 95% of the cost was a clustered index scan, and realized the predicate was non-sargable because we wrapped a date column in a function. I rewrote it, added a covering index, and response time dropped from 18 seconds to 1.2 seconds. That story hits indexing, sargability, and observability. Another story could focus on Azure. We launched a feature with unpredictable usage, so we deployed the database on Azure SQL Serverless with minimum 0.5 vcores, maximum 4. When adoption stabilized, we moved to general-purpose 4 vcores and enabled automatic tuning to manage indexes. Query Store alerted us to a plan regression after a deployment, so we forced the previous plan while we fixed the code. This shows you understand service tiers, scaling, and automation. Have a stats maintenance talking point. Our order table grew past 200 million rows, so auto-update stats lagged. We scheduled a nightly job running update statistics, orders with full scan, and dropped fragmentation under 10%. That stabilized query plans and prevented spill-heavy hash joins. And a set-based thinking story. A stored procedure processed invoices with a cursor, taking 30 minutes. I rewrote it as a single set-based update with a window function, and it ran in 90 seconds. Wrap up by emphasizing collaboration. Performance isn't a hero exercise. You work with DBAS, SRES, and developers to identify the highest value fixes. Mention using Query Store baselines, Azure Monitor alerts, and automated tests to catch regressions early. Interviewers love when you talk about measuring before and after. We reduced CPU by 40%, or we saved $400 per month by scaling down after optimizing. Performance work becomes tangible when you tie it to dollars and time. Closing thoughts. SQL optimization isn't magic. It's a set of repeatable habits. Understand data distribution, provide the right indexes, keep predicates sargable, maintain stats, favor set-based logic, monitor the workload, and choose the proper Azure tier. With those habits, you can walk into interviews confident. When someone asks, "How would you tune a slow query?" you respond with a process, capture the plan, analyze operators, adjust indexes or predicates, retest, monitor. When they ask about Azure options, you describe the trade-offs between general purpose, business critical, hyperscale, and serverless, plus features like automatic tuning and read replicas. Use this guide as a practice script. Read it aloud, pause after each section, and imagine a follow-up question. Maybe you get asked to explain covering indexes again, or to choose between a row store and column store. Maybe you're asked how to migrate a noisy on-prem workload to Azure SQL. The more you rehearse, the more natural those answers become. Good luck on the interviews. You've got this. Table design and normalization pragmatism. Index conversations often assume the table design is already solid, but structure matters just as much. Interviewers sometimes ask when you'd denormalize a table or add a summary table. Explain that you start with third normal form designs to avoid update anomalies, then selectively denormalize when queries repeatedly join the same tables. For instance, if your orders table always joins to customers solely to retrieve loyalty level, you might duplicate that field in orders maintained via trigger or application logic, so the OLTP query touches one table. Emphasize that denormalization is coupled with disciplined maintenance and often pairs with filtered indexes, so only the hot subset benefits. Discuss partitioning as a table design tool. Range partitioning by order date allows you to archive old partitions or switch them out quickly. In Azure SQL, partition tables let you rebuild indexes by partition, reducing maintenance windows. The key is to align your clustered index with the partition key so the engine can eliminate partitions during scans. Talk through a scenario. A 5-year order history table partitioned monthly. End-of-month jobs switch out the oldest partition to cheaper storage while new partitions slide in. That story shows you understand both performance and operations. Memory grants, tempDB, and spill avoidance. Execution plans require memory to sort, hash, or aggregate data. SQL Server estimates the needed memory based on statistics. When it guesses low, operators spill to tempDB, which hurts performance. Interviewers appreciate when you say you watch for the yellow warning icon that reads hash warning or sort warning, meaning a spill occurred. The fix might be as simple as updating statistics or rewriting the query to aggregate less data. In Azure SQL, you also monitor tempDB usage via DMVs or Azure Monitor Metrics, ensuring you aren't saturating I/O. Another angle is memory grant feedback, available in newer SQL Server and Azure SQL versions. The engine learns from previous executions and adjusts grants for subsequent runs. When you combine that with Query Store, you can see grant tuning over time. Still, you don't rely solely on automation. You limit result sets, paginate in the application layer, and avoid select star. Bring up examples of replacing select star with explicit column lists to reduce row size by 40%, which in turn lowered memory grants and prevented spills. Connection layer and application patterns. Even the best query falls apart if the application mismanages connections or transactions. As a .NET developer, you're expected to use connection pooling and short-lived connections. Mention SQL connection in a using statement so connections return to the pool quickly. Discuss how long-running transactions hold locks, causing blocking, so you keep business logic in the application layer and keep database transactions as tight as possible. Also talk about batching. Instead of sending 10,000 individual insert statements, you use table-valued parameters or bulk insert APIs to reduce round trips and transaction log pressure. Explain how enabling multiple active result sets, MARS, can create hidden concurrency issues, so you favor asynchronous programming with awaited calls rather than overlapping commands on one connection. Interviewers like hearing that you profile queries from the app side using Application Insights or Azure Monitor to correlate spikes with specific endpoints. Automatic Tuning Deep Dive. Earlier we mentioned automatic tuning, now give it more substance. Azure SQL's automatic index management watches query store data and proposes create or drop index actions. Each recommendation includes the estimated improvement and, once applied, a verification period. If performance regresses, Azure automatically reverts the change. Describe how you'd enable automatic tuning via Portal, ARM template, or TSQL, altered database. Current set automatic tuning, force last good, plan equals on, create index equals on, drop index equals on. Emphasize that you still review suggested indexes, especially in write-heavy systems where too many indexes hurt DML performance. Automatic plan correction is equally powerful. When Query Store detects that a recent plan for a query performs worse than a previous plan, Azure can force the last known good plan. This protects you from parameter sniffing or statistics changes causing regressions. Share a hypothetical. After deploying a new version of an API, CPU doubled. Query Store showed a new plan using a hash match instead of the previous nested loop. Automatic tuning forced the old plan, buying you time to investigate without user impact. Cost management and scaling stories. Cloud literacy isn't just knowing which tier exists, it's telling stories about scaling decisions. Suppose you inherited a database on business-critical 16 vCores because the previous team feared slow storage. After analyzing query store and weights, you discovered most CPU usage came from a few poorly indexed reporting queries. You added covering indexes and moved those queries to a read replica. With the workload optimized, you scaled down to general-purpose 8 vCores, saving several $100s per month. That narrative shows you prefer optimization before brute force scaling. Another story could involve auto-scaling elastic pools. Imagine multiple microservices each with modest databases whose peaks occur at different times. You move them into an elastic pool, monitor DTU or vCore consumption, and adjust pool size. When one service experiences a seasonal spike, you temporarily scale the pool, parallel to scaling the app tier. Mention automation options like Azure Functions, responding to monitor alerts to trigger scale operations via REST or ARM. Practice regimen and hands-on drills. The fastest way to internalize these topics is deliberate practice. Outline a regimen, spin up an Azure SQL database, restore the AdventureWorks sample, and enable Query Store. Run a slow query, capture the plan, then add an index and compare before and after metrics. Next, intentionally break a predicate by wrapping a column in a function, observe the scan, and fix it. Then enable automatic tuning and review its recommendations after a day of workload simulation via SQL query stress. Extend practice into the cloud tier domain. Create both serverless and provisioned databases, run the same workload, and watch how compute pauses in serverless mode. Trigger a scale-up via the portal or CLI, noting the brief disconnects. Monitor metrics in Azure SQL Insights, capture weights, and export them to a dashboard. When interviewers ask how you stay sharp, describing this personal lab instantly differentiates you. Advanced topics you can mention briefly. You don't need to be an expert in every edge case, but sprinkling advanced topics into interviews shows depth. Mention table-valued parameters as a way to send sets from .NET without repeated round trips. Reference Stretch Database or Azure Synapse link when discussing archival strategies. Bring up ledger tables if security and tamper evidence come up. None of these require deep dives, but acknowledging their existence proves you keep up with the ecosystem. Another advanced angle is security versus performance. Row-level security can introduce predicate functions on every query, so you plan indexes around the security predicate columns. Always encrypted can prevent the server from seeing actual values, making some operations impossible or unsargable. Explaining that trade-off demonstrates maturity. Building interview narratives. Close your preparation by scripting narratives for common question types. For tell me about diagnosing a slow query, have a beginning, alert from monitoring, middle, plan analysis, stats update, index change, and end, measurable improvement, lesson learned. For how do you size Azure SQL, describe reviewing workload metrics, testing on different tiers, using Query Store to see CPU per query, then choosing a tier plus an auto-scale strategy. For what do you do after a deployment? Talk about using Query Store automatic tuning reports, extended events, and Azure monitor alerts to confirm stability. Record yourself explaining these stories. Listen for jargon overload or missing steps. Aim for clear sequencing: problem, investigation, solution, validation. Interviews reward clarity as much as expertise. Step-by-step diagnostic workflow. To make all of this stick, memorize a repeatable workflow. Step 1. Confirm the symptom. Is the issue high CPU, slow response time, blocking, or errors? Grab metrics from Azure Monitor or sis.dm _db_resource_stats so you're not chasing ghosts. Step 2. Identify the top offending queries using Query Store, sis.dm _exec_query_stats, or Azure SQL Insights. You're looking for outliers in duration, CPU, or logical reads. Step 3. Capture the actual execution plan for the worst offender. In Azure Data Studio, run the query with Include Actual Plan enabled. In production, use Query Store or set statistics XML on to avoid rerunning heavy statements. Step 4. Inspect operators. Are there table scans where you expected seeks? Are there key lookups executed millions of times? Are there sort or hash match operators spilling to tempDB? Step 5. Map those operators back to schema choices. If a scan appears, perhaps an index is missing or the predicate is non-sargable. If a key lookup appears thousands of times, maybe you need to include the columns being looked up. Step 6. Verify data distribution by checking statistics and row counts. Use dbcc show statistics or sys.dm _db _stats _properties to ensure the histogram reflects reality. Step 7. Apply targeted fixes. That might mean creating or adjusting an index, rewriting a query, updating statistics, or changing isolation level. Step 8. Validate. Rerun the query, compare metrics, and watch Query Store to confirm regression risk. Step 9. Document and automate. Update runbooks, add alerts, or script index creation so the fix survives future deployments. This 9-step script becomes your go-to answer for walk me through how you'd troubleshoot a slow query. Quick reference glossary and interview prompts. Sometimes interviews devolve into terminology quizzes. Having a crisp glossary helps. Define covering index, a non-clustered index that supplies all columns a query needs, eliminating lookups. Define parameter sniffing, the optimizer basing a cached plan on initial parameter values that may not represent future executions. Define sargable, a predicate that lets the optimizer seek into an index, usually because the column is isolated on one side of the comparison. Define RBAR, a reminder to favor set-based operations over row-by-row logic. Add Azure-specific definitions. Service tier, the performance and availability bundle, general purpose, business critical, hyperscale, serverless, chosen based on workload. Automatic tuning, Azure SQL's feature that forces last good plans and manages indexes based on telemetry. Read Replica, a secondary database that receives asynchronous log replication for read-only workloads. Elastic Pool, a shared compute container hosting multiple databases with bursty workloads. Pair each definition with a prompt. After explaining sargability, prompt yourself. Give an example of fixing a non-sargable predicate. After defining automatic tuning, answer the follow-up. When would you leave automatic index creation disabled? Answer, when the workload is extremely write-heavy or tightly controlled. After describing read replicas, anticipate, how do you handle read-after-write consistency? Answer, inform the application about eventual consistency or route critical reads to the primary. Practicing these micro Q&A pairs cements the language and the reasoning you'll need under pressure. Add a final habit. After every fix, snapshot metrics and compare a week later. Trends matter more than single runs. When you tell interviewers that you revisit metrics to ensure the system stays healthy, you demonstrate ownership beyond the initial hero moment.